Let's now look at these three review problems concerning conjugate and conjugation and these functions involving complex numbers. First, we'll prove that the conjugate of e to the z is equal to e to the z conjugate. To do this, we observe that e to the z conjugate, by definition, this is the summation of n equals 0 to infinity of z to the n over n factorial, whole thing conjugate. Now, one of our theorems about conjugates is that if I have the sum underneath the conjugate sign, I could instead take the sum of the conjugates. So sum from n equals 0 to infinity of z to the n over n factorial, where I have the conjugate of this fraction. Another theorem says that when I have multiplication or division, I can introduce the conjugates. So this is equal to the sum from n equals 0 to infinity of z to the n conjugate divided by n factorial conjugate. Now, n factorial conjugate is just n factorial. Any real number, the conjugate of any real number, like n factorial, is itself. So the conjugate disappears on the denominator. On the numerator, z to the n conjugate is the same thing as z conjugate to the nth power. Again, using our rule for conjugation and multiplication. And so this last series is the exact same thing as the first series, except I have e to the z conjugate, where the conjugate sign is now in the exponent. So that's the proof of number 1. To prove number 2, that sign of z conjugate is the same thing as the sign of z conjugate, with the conjugate inside of the sine function, we do pretty much the definition of the sine function. So sine of z conjugate, by definition, that is e to the iz minus e to the negative iz divided by 2I, whole thing conjugate. And so using our rules that we've used before, we have that this is e to the iz minus e to the negative iz, the numerator conjugate, divided by 2I conjugate. Okay, now the denominator is easy. The conjugate of a pure imaginary number, 0 plus 2I, is just 0 minus 2I. So I have a negative 2I in the bottom. On top, I have the difference of two complex numbers conjugate. And so that's the first complex number, e to the iz conjugate, minus the second complex number, e to the negative iz conjugate. And by the first part that we did in red, the first term is e to the I times z conjugate minus e to the negative I times z conjugate divided by negative 2I. Okay, so here I have a product, and so I can split up the conjugate sign one more time. So I conjugate times z conjugate minus e to the negative I conjugate times z conjugate, all divided by negative 2I. Okay, so the last steps we have I conjugate, again, is negative I. So I have e to the negative I times z conjugate minus e to the plus I times z conjugate, taking the conjugates of I and negative I, divided by negative 2I. Okay, so let me clear off these intermediate steps and carry this over to the start. So far, e to the iz is equal to e to the negative iz conjugate minus e to the izz conjugate. This is equal to, if I multiply top and bottom by negative 1, I get e to the iz conjugate minus e to the negative iz conjugate divided by 2I. That's just multiplying the top and the bottom by negative 1. And by definition, this is equal to the sine of z conjugate. So the sine function and the conjugate function also commute. Finally, we proved the third one for cosine, and the proof will be very similar. So I'm not going to be quite as detailed on this one, but it'll be very similar to what we just did. Cosine of z conjugate. By definition, this is equal to e to the iz plus e to the negative iz divided by 2, whole thing conjugate. And so this is equal to e to the iz conjugate plus e to the negative iz conjugate divided by 2 conjugate. Well, 2 conjugate is just itself, so we just have 2 on the bottom. On top, we have e to the iz conjugate plus e to the negative iz conjugate. And so we did this before. E to the iz conjugate is e to the negative I times z conjugate, because the conjugate of I is negative I. Likewise, for the second term, the conjugate of negative I is plus I. So that's I z conjugate divided by 2. And we notice that except for just reversing which one comes first, I have the same terms that I would have in cosine of z conjugate. With the cosmetic change that the second term is first and the first term is second. So except for that cosmetic change, we have cosine of z conjugate, and so that is the end of the proof. So this is an exercise in just simply using the arithmetic of complex numbers.